Hi, everyone, and welcome to another measurement instrumentation class. In the previous class, we finished the errors and type of errors and how we measure those errors and calculate those errors, such as relative and absolute errors and mean, standard deviation, and so on. Today, we're going to start with the instruments. Our first instrument that we want to study would be voltmeters. We will start with voltmeters, then go through ammeters, and then finally watt meters or power measurement tools. And we will go through an ideal. We already know how an ideal voltmeter or ammeter works. We will go through a real world ammeter and voltmeter and discuss their errors and the waste that we have inside an ammeter or voltmeter, the internal resistance, how we calculate that internal resistance, and also how we can actually measure different voltage. Like if we want to measure a higher voltage, how can we modify an existing voltmeter to be able to measure higher voltages? So without further ado, let's start with the voltmeters. The first type of voltmeter is the analog voltmeter. Since these have become obsolete, you will still see them a lot in some power plants, and but they are mainly being replaced by digital ones. And there are a couple of reasons. The digital ones, you can directly get the data and transfer that data and do data analysis on that. An analog one, you cannot incorporate that in, for example, a smart grid or a microgrid if you want to have something like that. Now, even the power meters have been replaced with digital ones right now, because you can easily transmit the data, you can store the data, you can process that data and manipulate it. That's one reason. The other reason is that these analog multimeters, they are reliable, most of them, but they tend to have errors. They have drift. And because they have mechanical elements such as a spring, if you put it on the shock, any sudden movement would cause an error and deflect that spring and cause a permanent error in the system. And also, it's prone to error when you put it in a magnetic field or on a high voltage. If you put it in a very high voltage, the internal coil would be destroyed. Today, I brought with me a analog multimeter. I want to show it so you can all see it. So this is an example of an analog meter that you would see. And you can see, even when I wobble it, you can see that the needle is moving. Okay, so imagine what happens if I throw it down, or put it on the shock or put a magnetic field on it. It's gonna create problems. Now, on this particular multimeter, you can see that you can measure the current, and you can also measure the voltage here. And we have different pins for measuring the current and for measuring the voltage. We also have a reset button on here as well to reset the system. And usually at the back, we have a screw. So you have a screw on the back that you can actually calibrate the system. So after a while, what happens is when you put too much voltage through this needle is going to move what we call drift. And when it's not connected to anything, it's not going to go back to zero. Okay. Therefore, we have to adjust that screw to be able to push it back to zero. So you have to constantly calibrate this. Again, it's going to be very, very sensitive to movement, to mechanical shock. Even if you do a measurement when it's standing up, and when you lie it down, you're going to maybe have some errors as well. And even if you hold it this way or upside down and do a measurement, you would see that it would show different results. And this is a very good one, but it's from the 80s, and I'm going to pass it around. The good thing about some of these, they don't require an external power supply, so you don't have to worry about changing the battery or anything. But for a digital multimeter, you need to change the battery. It needs an external power source to be able to operate. But these multimeters, they don't need an external power source, and I'll explain why. in the later slide. Yes.
Called a passive multimeter?
Yes, yes, exactly. Yep. Now, another type of, and let me just give me a second to go back. Now, the way that a analog DC ammeter voltmeter works is it has a permanent magnet and it has a coil. It's a rotating coil. And what happens is when you put current, and I've already mentioned this, when you put current through that coil, it generates a magnetic field. And that magnetic field cancels the magnetic field from the permanent magnet and creates the movement. Now, again, if you put too much voltage or too much current on the coil, you're going to destroy the coil. You're going to burn the copper insulation around it. So it has some limitation. And I'll explain what we can do to minimize those limitations. And again, as you can see, we don't have any external power because this ammeter voltmeter is going to be powered with the input signal, the measured signal that we get. Now, also with me, I brought another type, which is an older type. And you can see here, this one is an ohm meter. So an ohm meter is a type, it works like a voltmeter and an ammeter. It uses the Ohm's law. And you put a voltage, a known voltage, on a resistor, and then you measure the current, and using the Ohm's law, you can determine its resistance. So you can see it shows the ohms and ohm meter. So this one, again, it's pretty heavy. And the reason it doesn't have external batteries, and to charge it, actually, it has a small crank. And you just turn it around and creates the power to be able to measure. So it has a small generator inside of it. So this is how it's actually powered. I think it's from the 70s or 60s, but yeah, you can take a look at it. And here you can see we connect the resistor that way. So back then, if they needed an external power, they would, be creative and work like and have a crank that you generate your own voltage, and therefore you don't require any batteries. But batteries in 56s were pretty expensive, and before that, they won't even last a week. And the chemical inside would, be spoiled and they will leak, so they would go with this solution. Okay. Do you have any questions about the ammeter or voltmeter? No? Okay. Yes, please.
Yes, a thermal relay, not a circuit breaker, but fuse.
Okay.
Instead of a mechanical reset.
So the mechanical reset here again is, yeah, it's a mechanical reset. Yeah, it's just repositions that. Yeah, it's not working like a relay. But if you take it apart, you would see under that is also another screw as well. So you can adjust how much, yeah. It actually controls the springs, movement. It's not like a relay or, yeah. But good question. Thank you. So before I get into the ammeter and voltmeter, I just want to give a quick reminder on how a voltmeter and ammeter work. So as you may recall from circuits 1, which is AC/DC analysis or electronics, the way that a voltmeter works is like this. If I have a resistor connected to a power source, a power supply, like a DC power supply, imagine this is 12 volts. And if I want to measure this voltage, I'm going to call it VR, or the resistor's voltage. Where should I put my voltmeter?
Across the
element you're trying to.
Perfect. I have to put it in parallel, yes, with the element that I want to measure its voltage. So voltmeter must always be in parallel with the element that I want to measure its voltage. What is the internal resistance of a voltmeter? Yes, it should be, ideally it should be infinite. Why? Because if it's small, it's going to pass a little bit of current, and therefore you're going to have a drop in the current passing through the resistor, and you're going to have a drop in the voltage, so you're not going to measure an accurate voltage, okay? So ideally, we want it to be infinite. And in an ideal situation, when it's infinite, means that actually the voltmeter acts like an open circuit. And an open circuit, when we have an open circuit, VR would be equal to the V of the voltmeter. I'm going to mention it by VV. Okay, so the resistance of a voltmeter, in an ideal situation, we want it to be equal to infinite. What about ammeter? How do I measure the current if I want to measure the current for this circuit?
Put it in series.
Perfect. I have to put it in series. So if this is my resistor, I have to put the ammeter here in series. So the ammeter should be in series, the voltmeter should be in parallel. And these are for ideal situations. Again, we never have an ideal ammeter or voltmeter. We always have an internal resistance for the ammeter and for the ohm meter. Now, for an ideal ammeter, I'm going to call Ri. What should the input current be? I'm sorry, input resistance. What is it for an ideal ammeter?
0.
0, perfect. Why is it 0? Because even a slight resistance for the ammeter creates a voltage drop on the ammeter and therefore reduces the amount of voltage that we put on the resistor, and therefore you can't get a correct reading on the ammeter, the current, and also the voltage. And there's another way, obviously. There's another reason as well. What is the current of the resistor and what is the current of the ammeter? What is the relation between the current passing through the resistor and the current passing through the ammeter? Just forget about the voltmeter for a second. What is IR relation to IA, or the ammeter?
It should be.
They should be equal. So again, imagine that voltmeter is ideal, meaning that the resistance is infinite, therefore the current passing the voltmeter is 0. So what is the current passing through the voltmeter? I'm going to call it IV. What is IV equal to?
Be very small.
Yes. Since the resistance is infinite, it's almost like an open circuit. Therefore, the current passing through it in an ideal situation is 0. Okay. What about its voltage, V of V? What is the relation between V of V and V of R, the resistor? They're the same. They're parallel. They share the same voltage. Now, what is the voltage of the ammeter? I'm going to call it VA. Why?
Yeah. Because there's no voltage drop across.
Perfect. There's no voltage drop. Voltage drop would be IR. And since if I put this point as C and D, VC is equal to VD because we have no voltage drop. Therefore, the difference between them is going to be 0, or V of the ammeter, which is VC minus VD, is going to be equal to 0. But in real world, it's not like this, and I'll explain it in the next slides as well. Now, for a DC meter movement, the meter may be modeled as a resistance. For example, and we're going to start with, again, an analog, and then we're going to go to digital, but most of the things are shared between them. For example, consider a meter that shows a full-scale deflection of the pointer at 50 millivolts, which is placed across the coil, and the resulting current through the coil is 1 milliamp. The corresponding resistance using Ohm's law is going to be V over I, which is 50 millivolts over 1 milliamp, gives us a resistance of 50 ohms. So this is the resistance of this coil. So the resistance of this coil is 50 ohms. And we model it as a resistance. Now, if I want to use it, let's start with an example. How does one use this meter to measure a maximum of 100 volts? So imagine we have this DC meter, analog meter. The internal resistance is 50 ohms, and I want to use this to measure 100 volts. Okay. Now let's see how it's done. So the resistance of the voltmeter itself, it's called a series resistance. This is the internal resistance of the system for a non-ideal voltmeter. And again, it's called series resistance. Now, if I want to find this series resistance, I want to find this series resistance to be able to find the resistance that I have in the coil. Forget about the previous one that I gave you already, the voltages. Imagine we don't have the voltages and we just want to directly find RS. So to do that, well, we can use the Ohm's law. We can say Vm is going to be equal to V times Rm over Rs plus Rm. Okay. Now, Vrm would be equal to Vm times Rs plus Rm. Am I correct? So Vrm would be V times Rm. V times Rm is going to be Vm Rs plus Vm Rm. Now we want to find Rs. So Vm Rs would be equal to Vm Rm plus Vrm. Therefore, Rs, I'm going to write the rest here, is going to be equal to Vm Rm plus Vrm over Vm. Or in other words, I can write Rm times Vm. I'm sorry, I did a little mistake here. VMRS is going to be VRM minus VRM. And this is minus. Sorry, I forgot to change the sign when I moved it to the other side. Because I moved this to the other side. So it's going to be negative VMRM over, let me write it like this. VMRM. So it's going to be V minus Vm times Rm over Vm. I think I've already included the proof over here. So Vm is going to be Vrm over Rm plus Rs, and we move it to the other side. And finally, Rs is going to be Rm, V minus Vm over Vm. So if we have the voltage of the source and the meter, and we also have the resistance, the load resistance, the meter resistance, we can find Rs. Now let's solve it for an example. Let's solve an example and I will give you another example. Right? So, for example, imagine that we have Rs. We want to find Rs. Rm is going to be equal to 50. V of the source was 100. Vm was 0.5. Let me write it here. Rm was 50. V is 100. And Vm is equal to 0.05. We want to find Rs. So if you use the equation, Rs will become 99,950 ohms or 99 kiloohms, close to 100 kiloohms. So you can see that the resistance of the multimeter, the internal resistance, should be extremely high, because if it's low, you're going to have a lot of current passing through that. Instead of the current going through the load resistor, it's going to go through the multimeter, and it's going to destroy the multimeter. Again, let me go back to the graph that I drew. Or I can draw it here. So if my voltmeter, again, has a low resistance, if the resistance is low, the current would pass through the voltmeter instead of the resistor. And if this resistance is very low, it's going to act like a short circuit. The majority of the current would pass through the voltmeter. And since this has little to no resistance, the coil, it's going to melt down the copper insulation and it's going to destroy it. Now, that's the reason that a voltmeter, when we want to use a voltmeter, we always need to have a resistor in series with it, which we call it the RM, the series resistor that we have. How many of you have been to the lab here downstairs for electronics? Okay. So this is the reason behind why we switch the terminals when we're going to go from a voltmeter to the ammeter. As you may remember, when you want to measure the voltmeter on a digital multimeter or any multimeter, you can see that it has a common point and a voltage or a current. So one is voltage, one is current. Even some of them have 2 voltage points and 1 current, or 2 currents point, 2 voltage points. When you connect it to them, you're connecting it to an internal resistor. And that's the reason if you forget to do that, you're going from an ammeter to a voltmeter, you're going to immediately damage or destroy the voltmeter. The older digital multimeters or the smaller ones, if you do that by mistake just once, it's going to destroy it. They have a fuse in the back that you can replace it, but most of them, it's completely, gone. Even the ones that we have on table, if you do that by mistakes, couple of times, put a large current through it, it's going to destroy the system. So that's the reason a voltmeter, ammeter, they use the same principle. Both of them use the same magnet, everything the same for an analog. The only difference is that for a voltmeter, we add a resistor here to protect it and to increase the internal resistance, as I mentioned. Okay? And this is going to be RS, and this is going to be its RM. I'm sorry, RM and RS. So this RM is usually very low because it's just a coil, a conductor, and this RS should be a very large resistor, usually in the hundreds of kiloohms, at least. And if we forget to switch that terminal, it's going to immediately damage a voltmeter, especially if it's these old ones. Now, the problem with the old ones, like the ones that I already showed you, is once you do this by mistake just once, it's going to destroy the coil, and you have to throw this out. And these were very expensive back then. You can see it has a lot of materials in it. But you could have also repaired them, but it's going to be like a painful process. I've actually opened them, and it's very difficult sometimes to repair them. And also, after repair, you have to calibrate it. You have to find the exact same coil. So it's not a straightforward, easy task. Now here you can see the screw for, can you see the screw when I change the screw? You can see I can change and calibrate it. Just, you can see it's, yeah, you can see the calibration with the screw. You can see I can calibrate it back to 0. Okay. Some of them have it also on the back, and calibrating is not an easy task. For digital multimeters, if you open one, I didn't bring one, you would see a fuse in the back. Usually the fuse blows to protect it because they have, but if the current is not that high, even the fuse may not blow and it's going to destroy your digital multimeter. So be careful. Again, on a digital multimeter, when you look on it, it has a COM point, it has a voltage and a current. And usually it says A and V, and this is the COM point. And when you want to measure the volts, you would put it between the COM and the voltage. And when you measure the current, you have to put it between these two. And adding it to the voltage, again, it adds this resistor to the voltmeter. Is it clear? Yes? Okay. Now, let me change the numbers and I'll give you a few minutes. I want you to do another one. So imagine we have the multimeter, the previous digital, analog multimeter. RM is 10. We want to measure a voltage of 200 volts. And VM, which is the voltage that it's on the coil itself, that is, let's say, 0.1 volts. I want you to find the appropriate resistor that we have to put in series to protect this and be able to measure that voltage of 100 volts. What is the result? I'm sorry?
19,509.
Approximately 2K, 20K. Okay, good. Now, let's do another exercise. What if I change this voltage instead of 200? Let's say I want to do 400. I want you to find RS again. So I'm doubling the voltage. I'm going from 200 to 400. So what happens if I go from 200 volts to 400 volts? What would the new RS be? Around 40. It's going to be around 40K. Okay. So increasing the voltage that we want to measure, by the way, this is the voltage that we want to measure. We have to increase the resistance. Okay. And this is actually how a DC voltmeter works as well. Instead of having one resistor, they have multiple resistors, and therefore they can measure a multiple range of DC voltages from low to high. Now, for this example, you can see that the resistors are 5K, 10K, 50K, and 100K. And with the 5K, you can measure up to 5 volts, 10K, 10 volts, 50K, 50 volts, and 100K, 100 volts. This is the exact thing that you see on these. There's a knob on here. You can see the knob. This is actually connected to this variable resistors. Yes. Let me show it here as well for a second. So again, on these, you would see there's a knob. And on the knob, you can see there's a different voltages that you can measure. And you can see the resistors, times 1, times 100, times. So these resistor actually gives you the different resistors that we have on these voltmeters. Now, again, if I want to measure the voltage in the output, V, we can just, this V would be our input voltage, and I can use a simple voltage divider to see how much voltage is on Rm, which shows the deflection on the needle, which is our coil. Now, if we want to measure AC voltage, and that was for DC voltage, what we need to do is simply we can add a, what is this, you remember? Yes, it's a full wave bridge, or in other words, a rectifier. A full wave bridge with a resistor. If we add that, what did a full wave bridge do? Do you remember? Yes, it redirected the current. Instead of having the positive negative cycle, we would have those ripples. Now, if you add a capacitor and a resistor, you can filter out and reduce the ripples as well and reduce the ripple factor. So adding a rectifier, we can measure AC voltage as well. So again, if you go back to this, it has AC and DC. There is another knob. Do you see the AC DC knob here on the right part? So if you click on this knob, and let me open my video. Now, if you look on this part, just give me a second to bring out the yeah, don't know what it does this, but yeah. Just give me a second to see if. Now, if you look on this again, you can see it has a knob that has AC and DC. Can you see it? I don't know if you can see it. You can see DC and AC. And it has DC negative and DC positive, because obviously if you put it in the reverse direction, it's going to put the needle in the opposite direction, force it to go to, and this one obviously doesn't have a negative. You can see if you put a negative, it's going to go on the opposite direction. It's going to damage the coil as well. So you have to be careful about the direction as well. But a digital multimeter adjusts itself automatically. You don't need to do that. Now, when you put it on AC, again, you would have the same resistors, but the only thing, you have to change the knob from AC to DC, and DC to AC. Now, it's the same for digital multimeter as well. You're going to say the exact same thing for a digital multimeter as well. Can we measure the DC voltage with an AC multimeter? This is a question. Can I measure the DC voltage with an AC voltmeter as well, or no? If I put it in the right direction.
Yeah.
Yes, you should be able to, but we don't. Why? Why? Perfect. Because of the forward bias of the diodes. If it's a silicon diode, it's about 0.7 each diode, and you're going to have 0.7 plus 0.7, 1.4 voltage. When we are measuring voltage DC, it's usually maximum like 12 volts. Imagine you're losing 2-3 volts of that in these resistors and these. So it's going to not going to be accurate as well. But an AC voltmeter, you're usually measuring like outlet voltage, 120, 130. Losing one is going to be 1%. But for DC voltage, imagine you want to measure something that it's 5 volts or even less than 2 volts. It's not going to measure anything less than 2.5 volts. Okay, so you're going to have a problem there. It's going to reduce that. But technically, if you have a very high DC voltage, like 300-400, you would be able. It's not recommended. Some of them, it would destroy, the capacitor and everything after that, the filter. But technically, you can do it if it doesn't have a very high-end one. Now, if we want to use the same thing for an ammeter, we can use the same multimeter that we have, the analog multimeter, but this time to measure the ammeter, the current. The only difference is in a voltmeter, you have to put the resistance is in series. For an ammeter, it's in parallel. Now, using a current divider equation, I can, again, the same thing that I did for a voltage divider, I can do it here for current divider to see how much current is passing through my resistor, parallel resistor, and also the coil. So I can measure the RS and RM, which is the current going through the coil. And using, again, current divider equation, I can get RS, which is going to be IM RM over I minus IM. Now, for the exact same problem that we had previously, imagine we want to measure the resistance of a ammeter. RM is, again, 50 ohms. The current that is passing through the coil is 0.001. Usually the currents are very low. And also the current that is going through the whole system, I, is 10 amps. So 10, it's going to be 0.001 times 50 over 10 minus 0.001 gives us an RS of 0.005 or 5 milliohms, which is a very low resistance. It's close to just having a wire, and therefore it's going to short circuit and it's going to almost bypass your multimeter's internal resistance, and which is very good because we want to have an extremely low resistance to put it in series and have minimal resistance in the system. Now let's calculate this. If we want to find a RS for I equal to 20 amps and internal resistance is 10 and IM is equal to 2 milliamps. So IM is 2 milliamps. RM is 10 ohms. And the current that we want to measure is 20 amps. We want to find RS. Okay, what is RS? Again, 0.002 because it's 2 milliamps times RM, which is 10, divided by IM, which is 20, minus 0.002. And what did you find? What is it?
1 million.
1 milliohms. Okay, yes. Close to 1 milliohms, yeah. Now, question. If I want to measure a higher current, do I have to reduce the resistance or increase the resistance? decrease it or increase it.
That would decrease.
Perfect. So for the 10 amp one, I needed a 5 milliohm resistor, yes? And if you imagine the resistors are the RM is the same, you're still gonna, reduce it. For a 20 amp, I needed a 1 milliohm. So the higher the current that we want to measure, the resistance that we want to have is going to be smaller. Why? Because eventually we want this to be a short circuit. We don't want to have any resistors. And for a voltmeter, we saw that we put the resistor in series. For the ammeter, we put it in parallel. So now you can see that reducing the resistor increases the amount of voltage that we can measure. So you can see for a 0.5 amp, we needed a 0.1 ohm resistor. For 1 amp, we need 0.05 ohms. For 5 amp, we need 0.01 ohms. And for 10 amp, we need 0.005 ohms or 5 milliohms. So the higher the current is we want to measure, you need a smaller resistor. It's exact opposite of the voltmeter. And you can see it again here as well on our voltmeter, ammeter. In here, again, the ammeter has few knobs. And if you change the knobs, you change the resistor. And for higher currents, you're going to put smaller resistors. Let me show this as well. So for the current meter, it's better to do it this way, better lighting. But for the current meter, again, you can see that we have different currents and different voltages. And for the current meter, you can see that by changing the resistors, and these resistors are in parallel with the system, you can increase the amount of current that you're measuring. Now, newer generation digital multimeters, they have an automatic system. They take a sample of the current. If it's too much, they automatically adjust the resistor. But older ones, you have to use a knob. But the ones that you saw in the lab, the ones on the table, they don't require changing and adjusting the knob. But if the current is above a certain level, you have to change the terminal because that automatically connects it to a different resistor. I don't know if you saw some of them have multiple terminals, and the reason is that because after a certain voltage, it's considered high voltage or high current, and you have to switch those terminals. Okay. Do you have any questions? No? Okay. This one? This one? Yeah. So you can see the voltmeter RM here is in series with all the resistors. For the ammeter, it's in parallel with all of them. So this and this, for example, are in parallel with each other. Okay. And this is actually a very good exercise. I want you to find RT, the total resistance, in this circuit when it's connected and this is connected to point A. I want you to find RT. What is RT? What is the total resistance between these 2 points? It's going to be what? 50.1? Who says it's 50.1? Okay. What did you get?
0.003.
0.003. Okay. I don't think it's going to be. No, it's not going to be that.
Getting
Yeah, all the time.
I can, just by looking at it, I could tell you. I don't need to calculate it.
Approximately.
Yeah, 0.999, something like that. So these two are in parallel. RT would be equal to, again, these are not connected. These two are just in parallel. It's going to be 50 times 0.1 over 50 plus 0.1. So when two resistors are in parallel, the total resistance is going to be the resistor of the smaller than the smallest one. So if you have a multiple choice in FE and this is like 51, 5, 10, 0.1, and 0.9, it's going to be 0.9. Okay, so this would be around 0.099, something like that. So a little bit smaller than this. So you can see that the 50 ohm doesn't make a lot of difference. Now, what about this one? If it's connected to point A, what is the total resistance got to be?
5,000.
Perfect. That's the reason this is 4,950, because combining it with the 50 plus the 50 gives you a 5 kilo ohm resistor. Okay. So 5, 10, 50, 100 kilo ohm. Okay.
So why don't we? Wait, is there like a specific reason why it has to be two different resistors, or is it like?
So that's a great question. That RM is, we don't have any control of that. And it's usually given in the data sheet. That's the resistor of the coil. Usually we put that, the second one, that you would have a round number, but yes, as you mentioned, it's not a particular one. But the thing is, on most of these multimeters, you can see it says 5K, 10K, 20K. And the way that they make it is by adding these two, it creates 10K, just to be easier to calculate it into system to
So
be
that
able.
RM is like an internal characteristic of the.
Yes, you would have
circuit
no,
itself.
yes, exactly. It's the resistor of that coil. That coil itself, it's copper, but it has a small resistor, and you have no control over that. But the resistor that we connect to that, this is RS, we have control over that.
Easier to work around that as opposed to just trying to.
Yes, yes, yes. You cannot, it's going to be very difficult.
So I wanted to ask, and you may have explained it already, but are VM and IM, are those internal characteristics of that as well?
Yes, VM and IM, perfect. Yes, yes, yes. VM and IM are the internal characteristics of that as well. And you can easily find VM and IM using Ohm's law. If I don't even give it to you and I give you V and I, you already have RS, you can find that. But the thing is, yes, completely. And there is a way that we can calculate VM as well. We usually give it a very small voltage without giving it the RS, and we measure that VM. But usually on these multimeters, if you look at the data sheet, they will give you VM, IM for different voltages. And it's a little different. So if the voltage increases, the VM increases a little bit. But in the exam, I will provide you with that information. But that's a great question. Yes, VM and IM is the amount of voltage and current passing through the coil at a specific voltage. And it's usually very small. Why? Because it's a copper, and you can't have too much, difference between the voltage on both sides. It's going to destroy the copper, you know what I mean? Or current. Yes, yes, exactly. Yeah, yeah. It's not a constant because it has, following a graph, but yeah, it's the characteristics of a system which would be given on a table. Yeah. Is it clear? Can I go to the next one? I'm sorry if I, explained it a little hard, but again, RM is the resistance of this. I'm going to call it RM, and VM and IM is the current passing through these. We don't have any control over these three, VM, RM, and IM. The only thing that we have control and we want to measure is RS. Okay. So we model this with the resistor, with the simple resistor, to make our job easier. The coil, we model it with the resistor to make our job easier. Now, what if we want to build an ohm meter? If we want to build an ohm meter, we use the voltmeter that we have. We measure the voltage and the current of a voltmeter, and therefore we can measure the resistance. As you know, according to Ohm's law, R is equal to V over I. Okay, so if I have an unknown resistor and I connect it to a 5-volt battery, and I measure the current, and the current tells me this is, let's say, 10 milliamps. So I have a known voltage. Always you must have a known voltage. Here it's like 1.5. Now what is the resistor going to be in this situation? It's going to be 5 divided by 10 milliamps. It's going to be 500 ohms, for example, in this case. If I'm not wrong, it's going to be 500 ohms. So you give it a known voltage and you just measure the current and you can determine the resistance. And digital multimeters do that internally. You also the analog multimeters can, some of them can do, some can't. And I already gave you the one with the crank. So when you know, spin the crank, it creates like 2 or 3 volts. And this just measures the current and multiplies that by the voltage. Already has a system that does it, and it measures the resistor. This has an option to give it external voltage as well. Some of them have, I think it's one of these lines. And using that, you can give it an external voltage to measure higher or smaller resistors as well. So if you can't generate enough power with the crank, you can give it an external power supply as well. Okay. Now, let me give you an example of this. So for this particular system, yes, I'm sorry. This is the unknown resistor.
I'm sorry?
This is Rx is the unknown resistor, the resistor that we want to measure. Yes, the ones
What's
that we.
the 50 ohm resistance? Is that like RS?
This is RS, perfect. RS, for example, and that is RM.
Oh, thank you.
Yeah. Now, for this one, I want to give you an example. Imagine that this is 0.1 ohms. And the current passing through this is, let's say, let me make 200 milliamps. What is Rx? So we measured the current as 200 milliamps. We want to find Rx. You can do a simple KVO in this loop. It's going to be 1.5 minus Rx times I, which is 0.2, minus 0.1 plus 50, or 50 plus 1 times 0.2. It's going to be equal to 0. So what did you find, by the way? What did you calculate for this? The-
-42.
yeah, I put too much current into it. I had to put a smaller current, but that is correct. What was it? Negative?
-22.
Yeah, or 42.6. I had to put like a small current. I put too much current in it. But imagine if this is 15. Let's change this to 15 to make the numbers work. So 15 minus 50 times 0.2 gives us 10 is equal to R times 0.2. So 5 is equal to R times 0.2. So R would be equal to 5 over 0.2, which gives us what? $25. Am I correct? 25 ohms. So please change this to 15 and the numbers would be correct. Okay, I think that's it for today. I don't think we can, start the next lecture. Again, I will post this first set of homeworks this weekend, and you're going to have 1 week, actually 10 days until the next weekend to complete and submit it. Thank you so much, and I would see you next week.